Okay. So, last week we started talking about the Bessel function, right? We had already defined the gamma function. And now the gamma function turned out very naturally in trying to solve the question of what is the Laplace transform of something like t to the p, where p is not necessarily an integer. And okay, so after we did this Bessel or this gamma function, we defined these Bessel functions. At least we wrote down a little bit of it. See, I think we just wrote down J0 so far. Is that right? Yeah. Okay, so let me recall what that was. So the Bessel function of order 0 is J0 of t. And what letter did I use? I used N. So it's actually going to be given as an infinite sum. It's an alternating series which only has even powers of t. Allow myself to introduce myself. And then we have here 2 to the 2n. Those are both 2's despite the difference. And then n factorial squared. Okay, did we leave anything out? No. Okay, so I think we wrote this down. And, well, the thing that made this seemingly random collection of symbols interesting is that it was a solution to a differential equation known as the Bessel equation of order 0, right, which looked like t squared y prime plus ty, that's y double prime, plus ty prime plus t squared y equals 0. So this is a solution to that equation. We didn't prove that, but that's what it turns out to be. All right, what else did we miss? Right, now at the end, I can't remember. Did we compute the Laplace transform of this yet?
No.
No? Okay, so well, maybe we should do that. It's actually not going to be very hard. We continue with our assumption that you're allowed to compute the Laplace transform of a series by taking the series of the Laplace transforms. That is, you take the Laplace transform of each term. So what is going to be the Laplace transform of a given term? So minus 1 to the n, t to the 2n over 2 to the 2n, n factorial squared. Well, don't let the fact that it looks complicated fool you. It's actually very, very easy. Why do I claim it's so easy? We'll see. N is some fixed, right? Fixed natural number of 0 here. That's a constant. That's a constant. That's a constant. Okay, there's a variable. But it's almost all constant, right? Okay, so I can pull this whole thing out. Minus 1 to the n over 2 to the 2n, n factorial squared. It times the Laplace transform of t to the 2n. Okay, so what's the Laplace transform of t to the 2n? Well, let's see. If I replace this t to the p with t to the n, there's my f, here's my L of f. What's the Laplace transform of t to the n? Okay, so t to the 2n is going to give you a Laplace transform of 2n factorial over s to the Now, it would be really nice if when we sum this up, we got something we actually recognize. So if we take the Laplace transform of the entire Bessel function of order 0, well, it's just going to be the sum of all these things. Oh, good. Okay, but we still don't know what that looks like. So when you don't know what an infinite series really looks like, sometimes it's useful to write down a few terms and then fiddle with it a little bit. Okay, so let's see. When n is 0, dead, 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 dead. Remember, 0 factorial is 1. Okay, all these things just become 1. Yeah. And then here you just get an s to the 1. So okay, the first term is 1 over s. That's not so bad. Okay, well, the minus 1 to the n just tells you it's an alternating series, so we know we're going to get a minus next. When n is 1, okay, we get 2 factorial, and then a, let's see, a 2 to the 2, and then a, well, that's 1 factorial squared. The 1 doesn't really show up much. And then this will become s cubed. So what do we have here on top? We have a
1.
Yeah, Courtney, are you canceling?
Mm-hmm.
Okay. So before we cancel, we have our 2 factorial, we have our 2 squared, and then we have our s to the s cubed. Okay, next term has to be a plus. Okay. And what's going to happen next? Well, let's see, that becomes a 2, so you get 4 factorial. And then we get up here, that'll be 2 to the 4th. And then this will be 2 factorial squared, which is 2 squared. And then you're going to have s to the 5th. You're going to try to make all my 2's have curls so that they don't mix up with the s's. And my 5's need to be really good 5's, so they don't miss with the s's. Okay, now I want to rewrite these things, and I will when we get to the next line. This form is not going to be the most useful form. Okay, and then we'll just write one down quickly. So the next one you can see is going to have to be 6 factorial over 2 to the, well, now there's 3 of them here, so that's 6 power, and then you get 6 squared. And then s to the 7th. Okay, then it's going to alternate from there. Okay, so what can I do with this? Well, the first thing I want to do is, this is very similar to a trick we were pulling last week. There's a 1 over s I can pull out of everything. All right, so I get a 1 minus, okay, so this is going to become an s squared. Now, this first one, you'll notice, of course, the 2 factorial is going to cancel with one of the 2's. Right? Because over 2 factorial is just 2. So I'm just going to get a 1/2. So let me write this as a half, and then I have 1 over s squared. I'm pulling them apart just to be suggestive. Not like, you know, dirty suggestive, just that kind of suggestive. All right. Now the next one, now what happens here? Well, first, there's a 4 factorial. So that's 4 times 3 times 2, and times 1. The 4 will actually cancel with that 2 squared. And the 2 well, I can cancel one of those 2's out. So on top, I'm going to write it this way. Of course, multiplying by 1 doesn't do anything, but it's there anyway. Now, what do I have left on the bottom? Well, I killed those 2 squareds, and I killed one of those 2's, right? So I have 2 cubed left. And I'm going to write it as 2 times 4. I can do that. And then I pulled out one of these s's, so I have 1 over s to the 4th. Now the next one, okay, I have a 6 factorial. That 6 will cancel with one of the 6's down here. The 4, I'm going to be able to, let's see, I have a 2 from here I can cancel with, and a 2 from here I can cancel with. The 2, another 2 I can cancel from here, so I just get left with these 4 2's on the bottom and that 1 6. So let's see, I left up there a 1, a 3, and a 5. And on the bottom, well, I left a 6, and then I had a 2 and a 4. And I get 1 over s to the 6th, and then this keeps going. And at this point, you probably can see the pattern. Make sure I didn't make any mistakes here. Look like they canceled properly. Yeah, Christina's happy, so I'm happy. Okay. Oh, and then we need, of course, a closed brace. Okay, now, so you can see what the pattern is going to be. You're just going to add an odd number on the top and then add an even number on the bottom. Okay, fine. Who cares about that pattern? Well, you should, because there's actually, this comes from a very nice little lemma, which, let me write this down. Where's my number? 4.8. So I'm going to have you guys prove this as homework. It's quite interesting.
Oh, we already have a 4.8.
We do?
Yes.
Oh dear. That means oh, did I add that in? Did I say, oh, I'm going to add this?
Probably.
Oh dear. Okay, that means all my numbering is off. Hold on, let me,
Oh, you know I did it just to screw you up.
oh dear. 9, 10, 11, 12, 13, 14. Okay, good. You wanted numbers, you said so don't complain if there's a lot of them. Okay, so we'll make this 4.9. All right. So, well, you guys are familiar with the binomial theorem, right? X plus y squared, you can do this, right? X squared plus 2xy plus y squared, you can do it for any n and so forth. Well, it turns out you can write down similar things when the exponent is not just a positive integer. Yeah. And actually, let me write it on the next line, I need a little space. So in the case where you have 1 plus x to the minus 1/2, you get 1 minus 1/2 times x plus 1 times 3 over 2 times 4 x squared minus 1 times 3 times 5 over 2 times 4 times 6 x cubed, and so on in the obvious method. So this will be on the next homework sheet. So this is nice. So this is a different version of the binomial theorem. Something different than what you're normally used to seeing with the binomial theorem anyway. Okay. We can immediately, though, apply it to our situation, right? Just what do I have to replace x with? 1 over s squared. So with s equals 1 over s squared, we get that, well, let's see, this was the Laplace transform of J0 t. And it's going to equal 1 over s times, okay, so this is going to be, if you like, 1 over the square root of 1 plus 1 over s squared. And if I turn this, if I move this s inside the radical, it turns into an s squared. And so I'll get s squared plus 1. This is quite remarkable. You remember at the beginning when we started doing our list of Laplace transforms, we had this t to the n and we said, it seems to make things slightly worse. Right? Not really bad, just slightly worse. And then we had the exponential function, whose Laplace transform was just 1 over s minus a. That was actually an improvement. But this is really quite something. You take this bizarrely defined function, right? It's defined as an infinite series. It just, what is this, 2 to the 2n factorial squared? I mean, it looks just like an absolute nightmare, but when you take that Laplace transform, you end up with a very reasonable function. This is the sort of thing that if you would have tried to guess what its inverse Laplace transform was, you'd have no chance, right? Yeah, how would I guess that? This is quite nice. All right. Let's try to improve our situation just a little bit. I'm curious, what if we scaled this t a little bit? So my next question is, what is the Laplace transform of J0 a times t? Right? Remember we had this same situation with e. We did the Laplace transform of e to the a t. Okay, so to compute this, I actually want to give you a more general result, which is to explain what happens when you scale any function. Okay, so we could have done this before, but okay, it's now 4.10. So if I'm going to take the Laplace transform of a function, but I scale the function by this parameter a. And what turns out is that it's equal to 1 over a times, now remember my convention, another way of writing the Laplace transform of a function little f is I use big F, right, not to be confused with the antiderivative. So this will be the Laplace transform of f, but instead of as a function of s, as if you treat it as a function of s over a. So you replace the variable s with s over a. Okay, so let's try to prove this. And the proof is just applying the definition of the Laplace transform. So L of f of a t, by definition, the integral from 0 to infinity, f of a t e to the minus st dt. And being graduates of Cap 1, or rather Cap 2, you might have a guess as to how to evaluate this. If you're struggling, I'll give you a hint. In the end, a 1 over a pops out. That might suggest a method. Don't need to use integration by parts. No. That's not what's going to pull the 1 over a out. If I was going to integrate something like e to the 2x, what would you do? You do substitution. What happens? You do u equals 2x. And then what happens? You pull a 1/2 out, right? Okay, so if we want to get a 1 over a out, boy, it looks like substitution u equals at sounds pretty darn good. Okay, so we do u equals at, so t, we're going to need the t, so t equals u over a, and du equals a dt, so dt is du over a. Okay, so what happens? So we get, well first, as when t is 0, u is 0, and as t goes to infinity, as long as a is positive, right? So let's assume a is positive in here. Okay, so as t goes to infinity, so does u, so it's still an integral from 0 to infinity. F of at becomes f of u. Uh-oh. Uh-oh. Oh dear. That was unintentional. Don't mean to write filth on the board. Okay. Now what happens to e to the minus st? Well, the t becomes a u over a. So I can write this as e to the minus s times u over a, or if you like, s over a times u. And then dt becomes du over a, so I need to pull a 1 over a out to get my du. And I claim this right here is exactly what we're looking for. This is 1 over a f of s over a. End of proof. Okay, why is that? Let me add some parentheses here. I'll draw it out. Okay, so first, 1 over a, that turns into 1 over a. Right? Next, you're integrating from 0 to infinity, a function with respect to u. And then you have e to the minus, okay, instead of an s, you have s over a times u. U. This is exactly the definition of the Laplace transform, only with respect to the variable s over a instead of s. So, there you go, f s over a. Okay, so this is nice because we can immediately write down the answer to our question. Okay, I'll just not go past here anymore. Okay, so I don't know if I gave this a number. Probably called it a corollary. Okay, so the Laplace transform of J0 at is, let's figure it out. Okay, if I put this a in, a 1 over a will come out, and then I have to replace my Laplace transform. Instead of an s, I get an s over a. So let's just do a little scratch work beneath it. Right? It's going to be 1 over a times 1 over the square root of, well, s has to become s over a. So s over a squared plus 1. Okay, so what happens? This becomes s squared over a squared. When you put the a under the radical, it becomes an a squared, and it'll kill this a squared. So you just get s squared plus, well, you got to multiply by a squared. S squared plus a squared. So 1 over the square root of s squared plus a squared. So now you know what to do if your Laplace transform spits out something that looks like this. It just comes from this nice Bessel function, scaled by a. Okay, so proof by lemma 4.10. Any questions? So, like I said, on the homework, what I will do is give you a lot of formulas to prove about the Laplace transform. So, for instance, well, this is a useful formula, right? You want to scale something. Okay, this happens. There are other things you might want to know, like for instance, what if I take the Laplace transform of a function, but I first multiply it by some power of t? So instead of the Laplace transform, of sine, I want t squared times sine. Yeah, okay, you can imagine having to do this. Okay, so there's a nice formula for doing this. I'll put this kind of thing on the homework. Right? Similarly, if you wanted to divide by a power of t, something like this. So much of what you can do with Laplace transforms is dependent on you just having a nice collection of formulas, so that when you apply the Laplace transform to a differential equation, and you start doing the algebraic manipulations and get it into a nice form, you can now immediately look at it and say, that's coming from this function. Right? You apply the inverse Laplace transform and see where it came from. And if you don't have a lot of these sort of tricks up your sleeve, then you get stuck a lot sooner. So I'll give you a bunch of those to prove, but I won't sit here and do them in class, because honestly, I could just keep on doing them for a long, long time. We could have a whole class where all we did was compute Laplace transforms, prove formulas about them. There's a lot to talk about. And I want to talk about other things eventually. Okay, so before we move on from the Bessel function, I want to replace this 0 with something more general. I think I called it a C on the first day. I'm going to call it an N today. It doesn't matter so much. So, more generally, write the Bessel function of order n. Copy some of this. Okay, so this is the way I'll write it out. Instead of writing it as an infinite sum, which we can do, let me just write it out with the first few terms. The pattern is pretty easy to see. So first, well, you'll notice when we wrote down lost my train of thought. When we wrote down the Bessel function, well, this was the Laplace transform, but the original version of it, we could have played a similar game where we factored out the power of t. So, or at least something we could have factored. Power t, not in that case because it was 0, but in general, this is what we can factor out. We're going to factor out a t to the n over 2 to the n. And, well, you remember we had this n factorial business. Well, this n factorial portion we could write as gamma of n plus 1. Remember, gamma of n plus 1 is n factorial. But this n doesn't have to be a natural number. Okay, this could be a half in this case. Okay. So we can factor this out all the time. And then we're going to be left with 1 minus t squared over 2 times 2n plus 2 plus t to the 4th over 2 times 4 times 2n plus 2 times 2n plus 4 minus plus dot dot dot. Okay, so what's going to happen? On the bottom, you're going to get 2, 4, 6, 8, right? You're going to keep adding these even numbers. And then you're also going to have 2n plus 2, 2n plus 4 added, and then 2n plus 6, and so forth. So it's very similar to what we got for J0. All right, so I'm going to give you some properties about these general Bessel functions. We won't take the time to prove them. There's a lot to do, and I might put, I probably won't have all of them on the homework, but I'll put a couple of them on the homework anyway for you to sort out. So this will come in, I think, 5 parts. So the first thing, we can define, well, not define, we can compute j sub a negative number, right, or the negative of n. N could be negative to start with. Simply by multiplying Jn of t by, oops, that should be an n. Put that down. So, for instance, if n is even, this is for, I guess what I would say for n a natural number. If n is even, then, well, this is going to just give you a 1. So it doesn't matter whether you're talking about j4 or j minus 4. If n is odd, j5 versus j minus 5, well, then it matters, but only up to a minus sign. Okay, now at this point you should stop me and say there's a problem.
What about for not natural numbers?
Just isn't true. Yeah. Yeah, can't do anything. But even just for natural numbers, there's a problem. Now, if I just said, okay, this is going to be a definition, this wouldn't be a problem. But I'm actually saying this is a true statement. There is a definitional problem here.
If you plug in n equals 4, j negative 4 will equal j 4.
If you plug n equal to 4, then j negative 4 equals j4. That's exactly true. That's not a problem. It's okay to have two things equal each other.
So how about n equals 0? You are saying n is irrational number.
Yeah, so say n equals 2.
No, how about n equals 0? So you are saying 0 is not irrational.
Well, this is a personal preference. I don't include 0 as a natural number. But if you put in, well, this is only, I'm only saying this is true for n equals, for positive numbers. That's all the statement is for. Okay, so for n natural numbers, right? 1, 2, 3, 4, 5. Now, it's not a problem if you put in 0 here, because it would just say j0 equals j0. Okay, that's true. Sorry. Let's say I put in n equals 2. So then this statement says that j minus 2 equals j2. My question to you is, what is j minus 2? Well, we have a definition, right? J minus 2 is, well, you do all this stuff.
We can't take the gamma function that we want.
Yeah, we got a problem here. Right? We did not define the gamma function when what? Well, what does the input have to be for the gamma function?
Greater than.
Greater than minus 1.
Greater than minus 1? Yeah. Okay, so so this is one of the statements that I'll put on the homework for you to prove. When I put it on the homework, right, this will give you a reason to look at it. I will show you how to define the gamma function. It's quite easy for negative numbers, right? For all negative numbers, and it's just going to be in terms of, you'll do it inductively, right? You'll just there'll be a way of shifting it up by 1 until it becomes positive. Okay. So there'll be a formula for how to actually do it. So this will make sense. Okay, so that's the first thing. There's a nice, these Bessel functions work really well as far as going from positive to negative. So usually you just need to worry about the positive ones. Up to a minus sign, then you know the negative ones. Okay, so here's kind of a nice inductive formula. if you want to know the n plus first Bessel function, you can write this in terms of the nth Bessel function and the n minus first Bessel function. So it becomes 2n over t times the nth Bessel function minus the n minus first Bessel function. That's a 1. So this is a nice little relation. The next one tells you how to take a derivative of the Bessel function and even multiplied by a power of t. So if you take the nth Bessel function multiplied by t to the n, and you take the derivative, this ends up actually just being, well, the t to the n stays, and amazingly all that happens is you decrease the index of the Bessel function, or the order of the Bessel function by 1. This is awfully peculiar. So all that happens when you take this derivative is that number goes down by 1. Okay. Now this next bit is going to be useful. Later on, we're going to, I think I mentioned, we're going to talk about complex numbers a little bit. This will be in the context of taking inverse Laplace transforms. And we'll come back to these Bessel functions when we do that, because there's a nice way of talking about them using complex numbers. And those of you who are in 481 actually might remember a problem on Bessel functions we had on the homework. And this function that I'll write down here was instrumental in that problem. So if we take the exponential, looks like e to the 1/2 times t times, well, I'll change the variable, make it a u. U minus 1 over u. It turns out that you can write this function as an infinite series, and it actually is infinite in 2 directions. Okay, so n goes from minus infinity to infinity. Okay, some of you may not have seen an infinite series that did that before. The coefficients are going to be the Bessel functions. So it looks like a power series, but it goes in 2 directions. Okay, sometimes you, what's the name for these things? A Laurent series. Okay, we'll come back to this. And so you look like you just have a nice power series here, only you can have negative exponents. And the coefficients end up being Bessel functions, which is very strange. Whenever you start seeing formulas like these show up, that tells you you found a good function. You found something right. You don't even know what it has to be useful for. You know it's got to be useful for something. Oh, come on. All right, and then the last thing is, I think I said at the beginning, it's that J and a T satisfies the differential equation. T squared y prime, double prime, plus t y prime, plus t squared minus n squared. So here n is the same n times y equals 0. So this is, of course, this was why Bessel was studying it originally, is he was looking for solutions to this differential equation. And I will probably, I think I will couple this formula here that you'll prove on the homework with having you, maybe I think I'll try to have you show that well, at least J0. Maybe not for all Jn, but at least show that J0 actually satisfies this. Right? Or derive that it does by using Laplace transforms. Because you can do that. And you can see why you would need a formula that handled this. Because, well, if you want to take the Laplace transform of this equation, you get something that we haven't had to deal with yet. Right? When we took Laplace transforms of differential equations, it always looked something like, I don't know, 3y prime plus 2y, I keep saying y prime, that's a double prime, you know, minus 4y equals, I don't know, g of t or something. Right? Now, this is a nice linear differential equation, but it's even better than just an arbitrary linear one because, well, an arbitrary linear says you have to have functions of t in front of the y's. But these are better than just functions of t's. These are constant functions, right? These just pull right outside of those Laplace transforms. You can't do that here. Right? You can't pull a t squared out. So you need to have, if you're going to take the Laplace transform of t squared y double prime, you need a formula that handles that sort of thing. Okay, so on the homework you get a lot of practice doing this. This would be quite good. I think you should get as much education on the homework on some of these as you do in the class. You just have to derive all the theory for yourselves. Isn't that nice? Okay. All right. What should we do next? Oh yeah, let me add in something. In part C, let me add in a little bit. So this formula is working for all n. I just want to write down in a particular case when n equals 0. Because when n equals 0, this t to the n goes away. So when n equals 0, you actually get a formula for the derivative of J0. And it just ends up equaling, what is that? J minus 1 of t. And by part A, what is J minus 1 of t? It's just minus J1 of t. So the derivative of J0 is minus J1. You like that, Kylie? There's something very aesthetically pleasing there. Let's see. Oh yeah, so what is this? Are we on 413? Well, it's already nice that we know the derivative of J0 is minus J1. But if we play this game backwards, we can actually now compute the Laplace transform of J1. So the Laplace transform of J1. Well, I won't tell you what the answer is. Let's figure it out, and then we'll add it to the statement. So let's see. The Laplace transform of J1 of t is, well, let's see, J1 of t is negative J0 of t prime. So this is the Laplace transform of negative J0 of t prime. Of course, the negative can come out. And then you're taking the Laplace transform of the derivative of a function. So we have a formula for that. Let's see. What's the formula? It's going to be S times the Laplace transform of J, not, minus the function evaluated at 0. And that's our formula. So let's let me write that down so you remember it. Okay, so remember the Laplace transform of f prime is s times the Laplace transform of f minus f at 0. Prove this? Ah, okay, but we know everything in here, or at least we could know everything in here. Let's see. S, now, what was the Laplace transform? This was of J0 is 1 over the square root of s squared plus 1. And then we need to know what J0 of 0 is. Oh dear. Let me figure that out. Let's remember J0 is this infinite sum minus 1 to the n, t to the 2n, over 2 to the 2n times n factorial squared. So if we plug in 0 for t, what do we get?
0.
I'm sorry, I didn't hear.
0.
0? You sure about that? Ling, yes, I'm very, very sure. The fact that I asked it that way suggests that you shouldn't be so sure, though, don't you think?
So you just plug in t equals 0.
Now I just plug in t equals 0, right? These all die. Does everybody agree? Karen, you agree? Well, let me ask you. If I said write down the first few terms of this, what's the first term? What's that? A 1. If you plug a 0 in for 1, well, that doesn't even make sense, does it? Okay, you're right. Normally when you plug a 0 in for t, you get 0 out. But the very first term here is when n is 0. You get t to 0 is 1, right? You can't plug 0 in for t in that case. In that case, everything is 1. Okay, so it goes 1 minus, and then a bunch of stuff with t's in it. Okay, the t's all die, so you end up with a 1. Okay, so J0 of 0 is 1. Fooled you. Okay. Well, let's see. First, this minus. I just put that inside to reverse, and I'll just reverse the order here. So 1 minus this, and then, well, I guess that is what it is, right? 1 minus 1s over the square root of s squared plus 1. A little more complicated than the J0, but still a reasonable function. And certainly not as bad as this infinite series would lead you to believe. Okay, so it's quite nice. And, well, now that you know J0 and you know J1, that gives you 2 of them. Now you can use part B here. If you want to know what J2 is, J2 you can get if you know J1 and J0. So, shall we try it? I didn't write this down, but it occurred to me that we could try it. Let's see. So J2 of t, well, I want the Laplace transform. So this is going to be, but you see here we're going to have a problem, aren't we? Okay, where are we going to have a problem computing?
Function times another function.
So by part B of the proposition, I can break it up like this. The 2n, that's just a constant, I can pull it out, but this 1 over t, I can't. Okay, so you already see we again need a formula that tells us what to do when we multiply a function by a power of t. So before we can solve this, you're going to need to do homework 3. Figure out what that is. Okay. All right, any questions at this point? Okay. I have a question for you. We won't answer it today, but is there a function? Okay, there's more to this sentence as you might suspect. Well, let me motivate this question before I finish it. When you're trying to solve a differential equation by using Laplace transforms, what's the method, right? You take the differential equation, you apply the Laplace transform, you now get an algebraic equation. You solve it for L of y, right? And then you try to figure out, okay, I have L of y over here, I have this nasty function over here. What function, right, gave me that as its Laplace transform? Right? And that's your y. Okay, so I have a really nasty function. Okay, I was sitting down, I did this thing to a differential equation, and I got L of y equals, and let me show you what the nasty function is. All right, so is there a function whose Laplace transform is 1? That was my nasty function that I got. Not 1 over s. Right? If it had been 1 over s, where would it have come from?
1.
It came from 1. Right? Okay, no, this was even easier, right? Right? 1 over s squared came from t. 1 over s came from 1. Next, the next step down, right? It's just 1. Where does that come from? All right, so you're looking for some function such that the integral from 0 to infinity of f of t e to the minus st dt equals exactly 1. That's all. Okay, so we're not going to answer this today, but we will start towards an answer. Because the answer is not... Well, strictly speaking, the answer is no. There is no function. But there is something called a generalized function that does it. Right? Now, our resident physicist may be the only one who has heard this name before, the Dirac delta function. Yeah? Okay, so he gets a big smile. That's good. Okay, so that'll be the answer to this question. There's something called the Dirac delta function, which is not really a function in the mathematical sense, but we can treat it like it is. And it's going to have a lot of properties that are really, really nice, and physicists know how to use it really well. And mathematicians just say, well, okay. So, but we'll work up to that. Before we get to there, so today I'll finish by doing something a little bit easier, something that actually is a function. And it's going to be called the unit step function. Not the stepsister or the stepmother, but the step function. So the unit step function is a terribly stupid function. It's going to look like this. You pick some number, say C, and so we're always going to assume C is positive. And you define the function to be 0 until you get to C. Yep. And then when you get to c, it's going to step up. Now how much is it going to step up?
1 unit.
By 1 unit. It's called the unit step function. Okay. So at c, it steps up to 1. And then from there, it stays at 1. Yeah. Terribly complicated thing. So because it's a unit step function, we'll call it the function u. And well, this c here, I can choose different c's and I get different functions. They all look the same, just change where it steps up. So I'll call it u sub c of t. Okay, and this is of course just a piecewise defined function. Right? It's going to be 0 or 1. It's 0 if t is less than c, and it's 1 if t is greater than or equal to c. Okay, well, just because something is easy to define doesn't mean that it's stupid or useless. 0 is very useful. Men are useful. The girls all smile with that one. Okay. So we can do a little bit. We can do a little bit more with these things. For instance, let's say I wanted to have a function that did this. Well, actually, no. Before I do that one, I'll show you how to reverse something. That'll be a better first step. This is a step up. Yeah. What if I wanted to step down? How could I step down?
You would replace the 0 with a 1 and the 1 with a 0.
That's true. How could I do it without referring to this definition, just by referring to the function itself? What's that? I didn't hear.
Minus.
Okay, so you're saying minus. Now, if I do a minus of a function, that does a vertical reflection. So that would take everything and reflect it across the axis.
And then add 1.
Ah, then add 1, right? Okay, so if I reflect it, this part goes down to -1. This part stays where it is. And if I add 1, then this will shift up to 1, and this part will shift back up to 0. Okay, so if I do 1 minus uc of t, right, then what do I get? I get, if that's c there, right, it's going to start up at 1, and then when you get to c, it's going to go down. Okay, so this is quite useful. Okay, so that's how you step down. Okay, now what if you you don't really want a staircase, but you want something that steps up and then maybe steps down later on? How can we do that? For instance, let's say I want to do. Okay, it's going to go to C, and then it's going to go to here, but at D, it's going to go back down. How could I do that? So this is a combination, right? This has both a step up and it has a step down.
You still do not want to alter the original function.
What's that? Yeah, I still don't want to mess with the. I just want to do everything in terms of these unit step functions, right? Not in terms of the definition. Well, let's see. This part comes from a UC. Just like I do. I went to a UC. Okay. This part came from a 1 minus UD. So you might consider, oh, just I don't know, add them together or something, right? UC plus 1 minus UD. So what would that do? What if you had UC plus 1 minus UD? Would that do all the right stuff? Okay, Zueling's saying no. Well, let's see.
UC minus UD.
UC minus UD.
Maybe.
Does that work?
Maybe.
Maybe. Okay, so we have two candidates. Any other candidates? Let's see. So between 0 and C, it's supposed to be 0. And D, D here, we can assume C, right, is less than D. The D is supposed to be a 1. So let's see, before you get to C, then that's giving you a 0.
UC minus D.
You think what? UC minus UD? No.
UC minus D.
Minus D?
Yeah, you just change the...
Oh, you think it's UC minus D.
So when you have T is less than C, so you will have 0. And the C is greater than C, less than D, you will have 1.
Could UC minus D work? No, why not? Well, this is a number again, right? And we know, well, first, okay, it's a real problem because C is less than D, so this would be a negative number, which we're not supposed to have. Okay, but maybe you meant D minus C. But even then we can't, because now, okay, you U some number, which means the graph has to look like this. So it can't be that one. Okay. So we're running out of time, so I was going to show you the answer today, but in fact, I want you now, since we've run out of time, why don't you think about this, and tomorrow you come back and you tell me what's the right answer.